crops. You would till cover crops in the spring. You would wait 2 weeks. You would till again, form beds, put down composted chicken manure as a fertilizer source, and then transplant, and then just continuously do that throughout the season. And so the idea of like soil fertility that I learned about was it. That was basically it. Like, you're using composted chicken manure for your NPK. You're using cover crops to help soil ecology or retain nutrients or have roots or penetrate deeper into the subsoil and bring out more nutrients. And that was basically the only way that people really like interacted with the sort of principles of farming agriculture. Is a little bit like substituting sort of conventional wisdom, using tillage, fertilizer, but using them in organic forms and using some other practices that were sort of seen as soil health benefits. And the problem with that is that it doesn't work in all contexts. So even in those contexts, we would have a lot of disease and insect pressure. Some crops would do better than others, but it was a little bit like, well, this is just the way it is. Every year is a little bit different, but there weren't really tools to evaluate exactly. It didn't feel like there were tools to evaluate why things went well and why things didn't go well. So that happened to our farm. We went through a period of like 2 years where we were kind of following that model, and the quality of our crops was like getting worse instead of better. I had this idea that crops farmed in an organic way, over time, all these like benchmarks would get better and soil health would improve and plant health would improve. But we saw sort of the opposite of that. And that was really alarming. We worked with a lot of different agronomists, and not a lot of people could help us. And so I started just like self-educating. So I don't think of myself as particularly expert in any field. It's just like when I started reading a lot, this was kind of the foundation that people who were thinking about soil health and plant health, this is kind of the information that's out there, and I've just kind of collated it. So the first slide is this, this is this concept of the plant health pyramid that John Campbell uses, which is really neat. So the basic idea is that there's sort of 4 stages to a healthy plant. And as farmers, our goal is to grow plants that are in these higher stages of plant health, because these are the plants that are creating more secondary compounds that have immune eliciting responses when we eat them. They're more nutrient dense, they grow healthier, they're more aesthetically pleasing, they have more aroma and flavor to them. So this concept of the plant health pyramid is just like a great visual for looking at kind of and evaluating where we are in our own management of the crops that we're growing. And we'll kind of come back to it a little bit later, but this is like the framework in which I now kind of look at the plants that I'm growing. Like, where on this pyramid do I feel like the plants that we're growing are? And a big part of that is just this idea that once we get into the higher levels of plant health, then we start seeing things like disease and pest resistance. We start seeing things like flavor and aroma increase, and we start seeing things more along the lines of like soil health benefits as well. So we start seeing organic matter in our soils increase. We start seeing more soil life, bacteria, fungi, protozoa, it's like communities, functional communities, and soil start to increase as well as the soil health, which is intangible. So this is just like a general overview, but all of this, like the new energy that gets entered into the system of soil comes through photosynthesis. And photosynthesis isn't a stagnant thing. Like it's extremely variable. So you can have plants that are photosynthesizing at a low level, and you can have plants that are photosynthesizing at a high level. And so just foundationally, what photosynthesis is the plant absorbs water through its roots, carbon dioxide through the air, through the leaves. It splits the water molecule, H2O, into H and OH. That's called water hydrolysis. And it combines it with the carbon molecule to create a simple sugar called C6H12O6, which is glucose. That's just the most basic form of what photosynthesis is. It's using the sun's energy to do that, and when it creates that sugar molecule, so it takes atmospheric carbon and it creates it into a solid form, or a liquid form in this case, it pumps that sugar into the soil profile and feeds microbes, so the mineralizers in the soil food web, which are the bacteria and the fungi. It feeds them these sugars, which can be more simple or more complex. And then these microbes mineralize the soil particles for all the nutrients that the plant needs. So that's calcium, phosphorus, nitrogen, molybdenum, zinc, all of the minerals that it needs. It gets from the soil profile, delivered to it through, mediated through these microbes. So when you have a plant that's photosynthesizing poorly, it's not able to exude enough sugars to feed the microbial communities in the soils in order to mineralize things appropriately. So a low photosynthesizing plant is an unhealthy one, and a high photosynthesizing plant is a healthy plant. So the simplest way that you can measure how well a plant is photosynthesizing is with a refractometer. And that is, do y'all know what a refractometer is? It's a little device about this big. It's often used in the wine industry, where they'll take a grape and crush it, and then you look through it, and the light passes through a prism through the liquid that is put on the slide and refracts it. Depending on the sugar content of that grape, there'll be like a little scale in the eyepiece, and it'll show you, it's like a scale of 0 to 35 or something. And basically, so that's what this leaf Brix chart, that's what this is showing. The Brix levels are on the top here. And so a very sort of quick and easy and cheap way of getting a understanding of how well your crop or plant is doing is by taking a leaf and crushing it in a garlic press and getting a drop of liquid on that little slide and looking at it and taking a reading of it. And so the general goal being to have plants that are brixing, plants having leaves that are brixing over 12. And so this kind of corresponds a little bit to the plant health pyramid as well, because as leaf brix increases, the susceptibility to different disease and insects goes down. So you have insects that have extremely simple digestive system properties, enzymes, mouth parts, like an aphid, for example. They can only digest plant matter, or they can only extract the plant sap from plants that are brixing below 5 or something like that. So as you kind of get more familiar with this sort of different signs of plant health, seeing aphids on your plant is also an indicator that you have really low Brix readings in your plant. And so as you increase Brix, you increase disease susceptibility. You increase the plant's ability to resist disease and insect pressure as well. And there's kind of this harsh, a lot of people who are looking at plant health have this kind of harsh interpretation of Brix, that if you're not producing food that is Brixing above 12, then it's not really considered food. It's basically considered garbage that insects and disease are on this earth to remove from the food supply. So that's a little bit of like a harsh way of looking at this. I think one way that bricks is helpful is just that it can kind of give us a snapshot of where we're at, and it doesn't say exactly what is missing from our practice, but it shows you if you're lacking or you need to do more investigation. So,
one question. You want to go to the store, pick up a leaf, squish it, look at it, tell you kind of like, oh, these greens are kind of solid, or these greens are kind of not solid.
yeah,
right?
it's a tool that you can use to evaluate food that you buy anywhere.
Word. And so it doesn't matter if it's even just a leaf, like if it's orange, or like whatever pulp from some food, you can do the same kind of thing.
Exactly. I would say with fresh food, that is generally something you can do. I don't know that you could use like a refractometer on like a Dole bottle of orange juice, because there's probably like what other
Added
sugars
sugars,
added to it.
yeah.
But yeah, you could absolutely use
Raw
that.
produce.
Raw produce, yeah, exactly.
Cool.
So yeah, that's a good question, because there are people that are, and organizations that are sort of in the business right now of creating what might be called like a bionutrient food meter, which is sort of this concept that's a little terrifying to me, but basically, the idea is that it's a more sophisticated refractometer. Basically, it's like you flash a light at a leaf or something, and it will evaluate the frequencies that come back to it, and you can kind of get a pretty good idea of the nutritional value of something. And the idea is that if we introduce this at like a consumer price point, that people will be going to like the farmer's market and just like, in real time evaluating what is, what the best carrot at the market is, and putting external pressure on farmers to change their practices to increase the quality of the food that they're growing, which in theory is a good thing. I mean, I think for like major, Walmart sells something like 50% of all the produce, in the country. And if you're putting external pressure on the producers for Walmart, that's probably a good thing. That probably will increase the quality of the food supply over time. But if you're like going to your local farmer's market and doing that, it seems a little harsh to be like a consumer and, bricksing somebody's carrot in real time and being like, this sucks. Like, what are you going to do about it? Kind of talked about this. So as photosynthetic efficiency goes up, then the plant is creating more and more complex molecules. So it starts with C6H12O6, glucose. It gets modified by adding nitrogen to it. It amino acids get turned into peptides. Peptides get turned into proteins. So a plant that is photosynthesizing really efficiently is taking all of the minerals that it's pulling in, and it's converting them into more and more complex molecules, ultimately into proteins. And enzyme production in a plant is also tied to this. So enzymes are kind of like box and wrenches. They're capable of doing like one job, but they can do it over and over and over again. And so a high photosynthesizing plant is creating lots of enzymes that's helping it to convert nitrogen into proteins, for example. A lot of enzymes are directly related to metals that are not generally considered a part of fertility regimes, and we're going to get into that in a little bit. But the example here is an element called molybdenum. And molybdenum is an anion. It's not required in large quantities in soils, but if the process of a plant converting nitrogen into a complete protein is completely dependent on molybdenum. So if you're not testing for molybdenum or seeing if it's in your soil, for foliar feeding it, then you're going to have a buildup of nitrate in your plant, and that's not going to be converted into protein. You'll have low photosynthetic efficiency, and you'll also be attracting insects to your plant. So this is an example of a soil test. This is what is sometimes referred to as an Albrecht style of mineral analysis. Two pages later.
It'll be quick.
I have another soil analysis. This is from Mississippi State, and it's just to kind of show the difference between what kind of soil test you can get at a sort of state university, and I believe the LSU one is actually even more limited than the MSU one, versus something from a private lab. This lab is Logan Labs. It's the lab that I prefer. I think it's sort of the best quality for the dollar spent. It's not that expensive. It's like $35 for this test, and you get a lot more useful information than something like from the MSU test. And also another sort of qualm I have with the state university testing is these graphs that they point out here. So these graphs are virtually meaningless. They don't. They're indicating very high levels of certain things, and when you learn how to interpret a soil test, you just like quickly realize how garbage this recommendation is. So I just wanted to make the case that when people start looking into soil health, the first thing that they generally do is they take a soil test and have it analyzed by a lab. And I would recommend, if you're going to do that, which I do that, and I think it's still important to do, that you send it to a lab that's going to do either a Albrecht style of mineral testing or a Reams style of testing, which is basically what you're looking at. So this is measuring, I forget, 12 different minerals, and William Albrecht was in the 1950s was a University of Montana or Missouri soil scientist, and he did this incredible research project where he looked at he actually looked at military service data and looked at where people in the country were rejected for service duty at varying rates, and he correlated people being rejected from the military for not being like healthy enough, quote unquote, with the soil type. That, you know, this was in an era when people were eating much more locally, so people's diet was reflecting more accurately what the sort of geological makeup of their soil is, and found that the so quote unquote healthiest population came from sort of the Midwestern area that had a specific balance of the 4 major cations in the soil. So soil minerals are either positively charged or negatively charged, and the soil particles, the clay, sand, silt that make up the type of soil that you have, they're all negatively charged, and organic matter, that's the other variable here. Organic matter is also negatively charged. And so when you have a negatively charged particle in the soil, it's able to hold onto a positively charged cation or mineral. And so his discovery basically was that you want 4 major cations, which are calcium, magnesium, potassium, and sodium. You want them to be in a specific ratio to each other. So you want calcium to be the most by volume, and so if you have like a sand particle that has like 100 different bonding sites, negatively charged bonding sites, you want 68% of them, plus or minus, to be filled with calcium. And then you want 12% of them to be filled with magnesium, 3% of them to be filled with potassium, and 0.5 to 1% with sodium. So this creates the sort of foundation for what healthy soil looks like across many different soil types. And that is generally referred to as the cation exchange capacity. Your soil has a unique amount of bonding sites to it that, again, are kind of made up or is a number that's unique to your soil based on the type of particles that you have in your soil. So sandy soils sort of famously have less bonding sites than clay soils. And so this is a report from my farm where we have very sandy soil, and sort of the 4th or 5th sort of number down, the total exchange capacity, that's what that number, 8.59, is not particularly low. It was much lower than when we started, but is low comparatively to soils that are more sort of clay-based in the Midwest, or have had more recent glaciation, or you can have CEC soils that are like river bottom land that are in the 30s, 40s, 50s, or whatever. So the CEC kind of tells you how large of a gas tank you have, how much nutrients your soil can hold in a stable form without sort of washing it away. And
you said that's what the total exchange is representing, is kind of the density, or like how many seats are in your soil. So your soil is like a bus. It's like you got a little bus that can hold 10 nutrients, or you got a big old bus that can hold 100 nutrients.
Exactly.
Gotcha.
Yep.
And this number represents
that number
of seats.
Exactly.
Okay.
Yep. So there's kind of a fancy calculation to translate, your exchange capacity with how much calcium, magnesium, potassium, and sodium you need. And I would recommend, there's lots of books that have been written about that, but a really good one is called The Intelligent Gardener, and it'll kind of give you it'll give you like a worksheet, basically. I have an example of one. It'll give you a worksheet basically of entering your numbers and calculating like how many pounds of a certain nutrient you need in order to balance your soil correctly. So it's a little bit beyond the purview of this presentation to kind of go into that, but it's the most important thing to sort of recognize when you're doing an Albrecht style of mineral balancing is that you're investigating specifically this principle of balancing the major cations in your soil. And for soils that are in the south, almost universally are very low in calcium. And soils that are low in calcium and high and sort of higher in magnesium from a ratio perspective are much, much tighter, more dense soils with less structure and less air movement through them, gas exchange through the soil profile. So they do things like, and this will be familiar to everyone, but they hold water. They hold water a lot more. Drainage is much poorer. They dry out very quickly, so they have very little water holding capacity. They go anaerobic much easier. So really establishing the correct amount of calcium in soils has this profound effect on soils, which helps to create more pore space in the soil profile and to alleviate things like water filtration and gas exchange with the environment, water holding capacity to a certain degree. So it's a very physical property that you can, that we as managers can help to alleviate the symptom of very tight soils by making sure that our calcium and magnesium ratios are correct. So that's a pretty foundational way of looking at soil health through this methodology of basically looking at the mineral levels in the soil. The other thing is that there's lots of micronutrients that are responsible for sort of higher levels of plant functioning. We looked at molybdenum, for an example, with the nitrogen reductase enzyme. So you can see in this soil test, like my molybdenum levels, the molybdenum levels are very low, like almost non-detect. So you can sort of imagine that if it's not in the plant, or if it's not in the soil, it's not going to be in the plant too. Yeah.
So, do these ratios vary from plant to plant, like the different types of soil?
To a degree. So, in general, I would say no. This is sort of a one-size-fits-all, and of course, there's lots of exceptions to that rule. But in general, for like most vegetables, most broadacre crops, like conventional crops, corn, soybeans, wheat, this is a basic framework that is a one-size-fits-all for that kind of cropping, those kinds of cropping systems. It gets more complex when you're looking at certain plants that have requirements for minerals that are more available at lower pHs. So, for example, blueberries are known to be grown in low pH soils, and it's a little bit of a misnomer. It's actually not that they like low pH soils per se. It's that they have high requirements for iron and manganese, and those are more available at pHs below like 5.5. So a lot of people grow blueberries in low pH soils. And I kind of jumped over this point, which is what you're making, is that there's a relationship between these cations and your pH. So when you balance minerals in this Albrecht style, you essentially create the conditions for pH in your soil to be 6.8, which is sort of regarded as the optimum pH for growing most crops. It's the pH that the most number of minerals are the most available for plant uptake. So when you look at things like blueberries that supposedly like low pH soils, it's not so much that they're like low pH soils, it's that they have high requirements for these minerals that are more available at low pH. So actually, like one management decision one could make growing blueberries is that you could increase the pH to something like 6, where more minerals are more broadly available, and then do things like foliar apply these minerals that they need in trace quantities, but they have higher requirements for than say like lettuce or tomatoes do.
So like your base level of soil throughout is that, but then like where you're growing blueberries, you're gonna add
Yeah, you could manage that a little bit differently than say you would manage like a greenhouse of tomatoes or something that would be much better off in like a more sort of closer to neutral pH where a broader range of minerals are more available. So you can, part of that is just management decisions, but it kind of comes down to like pH it's an indicator of, we talk about how like CC is sort of the size of your gas tank and pH is like how much gas you have in the tank. So with a low pH, that's basically indicating that you have low cations. It doesn't tell you which cations are low. If it's calcium, magnesium, potassium, or sodium, but it's saying that there is not a lot of one of those, because when you bring those up to the appropriate levels, the pH levels out at 6.2. Yeah.
If you had an unbalanced soil and you added something back in to try to balance, how long are you waiting before you're retesting it to check the balance again?
I do every 3 years. Some people do every 6 months. Some people do every year. In general, I think people over-test in this way. I think it's, the test is not perfect, and you can send the same test to 2 different labs and get different results. So this is not like precision. It's a little bit more looking to see where the major deficiencies are, trying to correct them in sort of a bigger way, and then letting things like biology and other sort of, more frequent, smaller dosage of fertilizing or something are going to kind of maintain things at a certain level. So I think like earlier on in farming, maybe I would do more like every year for like the first 3 or 4 years, and then after that, I think things don't change that quickly. You can kind of stretch that out longer, and you're going to have a little bit more of a buffer zone to work with. The sort of caveat to that is that the anions, so we talked about the cations, which are held onto the soil surface. Anions are negatively charged and are not held onto soil surface. So they're more prone to leaching, getting washed through soil. So the major sort of anions are sulfur, and then like any nitrogen that's being added is often converted to nitrate form in the soil, and that's very easily leachable. And then there's a number of other things like, boron is also molybdenum. We talked about these are things that your soil is not going to hold on to very well. Unless you have sort of high organic matter soils, then you have some buffering capacity to hold on to those things. So adding those things in like more frequent, sort of smaller doses, more frequently over time is one sort of strategy that you can use to kind of mitigate against that. But that is the other side of this. We're balancing the major cations, but you also still need these anions too. And sulfur is very important. Crucial element in protein synthesis in plants as well. So that's sort of that looks at soil health through this one prism of taking a test, extracting, exposing it to a weak acid, and seeing what gets extracted from the soil colloids, what minerals are released in that way. So it's one way of looking at what is happening in our soils. And it's more sort of chemistry based. The sort of next way that we can look at soils is through a biological lens. So the soil food web is a term that was coined by the biologist Elaine Ingham, and what Albrecht did for soil mineral balancing, she sort of did for soil biological balancing. So she has created and sort of standardized a way of looking at soil using a microscope, counting, through a dilution process, being able to count the individual microorganisms in that soil, and then extrapolating total quantities of those microorganisms in soil, and also the ratios between the different organisms throughout that soil profile. So her this is a major contribution to understanding soil, and not one that is even to this day like wildly recognized by sort of agriculture writ large. But she standardized this process of basically looking at what she calls the 4 functional groups. And so you have 2 that are mineralizers, that's the bacteria and the fungi, and then you have 2 that are nutrient cyclers. They're the ones that are consuming bacteria and fungi, and basically through their consumption, digestion, and pooping, are creating minerals in a plant available form that are much easier for the plant to absorb, much easier for them to assimilate into their growth habit. And we look at modern agriculture generally feeds plants simple ions like calcium nitrate or various forms of phosphate, which the plant is absorbing directly, or sometimes it's getting mitigated through the biological communities in the soil. But a plant can absorb simple ions like nitrate. I mean, this is how like greenhouse or hydroponics work. They're just putting simple ions into the water. They get absorbed into the plant. But those ions are they're simple to absorb, but not simple to convert into sort of these higher orders of plant matter, or the conversion of nitrate into protein, for example. Whereas it costs the plant a lot of energy in order to convert those things. Whereas if we have these different functional groups in the soil food web, they're basically creating nutrients in a plant available form. Like they're creating amino acids in the soil which are much more easy to convert into complete proteins than simply nitrate is. So her big discovery and what she teaches now is that it doesn't really matter, like the mineral levels in the soil don't actually matter. What matters is, do you have these 4 functional groups? And so you basically do an evaluation of your soil, and you compare that to the soil, like a native habitat soil that's trying to grow plants that are similar to the ones that you are growing for sort of agricultural commodities. So soils get more, as they get more complicated when they're supporting sort of higher forms of life. For example, generally tend to be more fungally dominant, whereas soils that have been recently disturbed generally have very little fungi in them, but have high bacteria populations. So when we think about agriculture, what we're doing is we're basically like tilling in crops, which is like this very extreme version of soil manipulation. It's basically, it has a lot of negative effects, like oxidizing the organic matter that's in the soil. It has the effect of killing fungi hyphae, the strands that are energy intensive to grow. They get chopped up, and you introduce a lot of oxygen, which is more beneficial for bacteria than it is for fungi. So through repeat tillage, you basically create the conditions for bacteria-dominated soils, which are good for growing things like weeds or very simple plants, but not so good for growing vegetables or fruit trees or Christmas trees or sporadic or crops like corn and soybeans. These have a sort of a correlation of fungi to bacteria ratios that's optimal for their conditions to be growing. So you can kind of look at the plant that you're trying to grow, sort of generally guess what the fungal to bacteria ratio it should be to be ideal, examine your soil using this process, looking at it under a microscope, and then figuring out what soil organisms are missing to create the optimum conditions to grow that plant. So it's a pretty elegant solution to, like, you can basically take any soil anywhere and evaluate it, see what microorganisms are missing, and then apply, generally the remedy for that is applying a compost that's been made in a certain way that creates a very microbial diverse mix of these 4 functional groups, and then either extracting them into water or creating a compost tea, or just applying that compost to your growing medium and reintroducing these soil microorganisms so that they can perform the role of nutrient cycling that is often very lacking in those soils.
Do these microorganisms essentially operate as a microbiota in that regard?
Yeah, it's exactly the same thing. In fact, most of our gut microbiota comes from soil microorganisms originally. So when you think about food that is grown in microbial-rich soils, a lot of the microorganisms that are in the soil are also on the leaf surfaces. So when we consume plants that haven't been sort of washed or treated with chlorine, then we're ingesting microorganisms that then continue to live in our gut and continue to process the food. So there's a large correlation between the diversity of the microorganisms that are in the soil that we're eating and the sort of gut flora health that we have in our bodies. For sure.
I got a quick question.
Yeah, no, I think
Making sure I thought this. All right, so this is kind of a new perspective for me, and I'm just trying to make sure I'm tracking it all. Kind of like I like looking at the bigger system. So plants photosynthesize to make the sugars to kind of feed all the microbes in the soil. Then the microbes are using that sugar to kind of step up different compounds, right? Going from a nitrate to an amino is saving labor for the plant, right? So the plant doesn't have to take in raw molecules, compounds, and convert them to aminos inside, which it does have processes for. But it's better if your little homie microbe over here does it for you. You give them some sugar, that's your little trade. And then you can look at, I guess there's what seems like to be this balance of all the cations in order to make the most nutrient-rich soils, but it's not necessarily pathway rich for the plant. It still may be the biological balance of functional groups in addition to the chemical balance of the thing. So it's both of these things being in balance, then offer best conditions for the plant. Internalized work.
that's exactly how I see it.
Okay. I was like, man, if I'm tracking this, okay.
Yeah.
So you got like little micro compost factories with the next level of function, like eating and pooping and concentrating.
Yeah, exactly. Yeah. So to be clear, plants don't grow in nature without microbial relationships. The mineral component of this is to make sure that the minerals that are essential for plant health are in the soil profile to begin with.